Hello everyone. Today we're gonna be doing the LeetCode daily. Hello Lucia, hi, welcome. So I shared the link. The problem is called the shortest path visiting all nodes. It's a hard one. And so you have an undirected connected graph of n nodes labeled from 0 to n-1. So pay attention, it is connected and undirected. You're given an array graph where graph of I is a list of all the nodes connected with node I by an edge. So yeah, this means that it is an adjacency list, which is usually a good representation to traverse the graph. So that's cool. Return the length of the shortest path that visits every node. You may start and stop at any node. You may revisit nodes multiple times, and you may reuse edges. All right. So that is interesting. Revisit nodes multiple times. So under some definitions, that is called a walk, or because usually paths are what's called simple. They do not repeat nodes, and walks do. That's why I use that term in the title. So here we get two examples. This is a tree, and here we go from one of the leaves to the root, then we go down and up, and then down again. So the length is 4, and there are 4 nodes. That's interesting. Well, notice this. The number of nodes is 12. So it's a tiny graph. That is already suspicious. And then, well, yeah, this is like the normal constraints on a graph. So for example, graph of I does not include I. That means there are no self loops, no edges that go from one node to the same. Then this means that it is undirected. Well, it is connected. And this makes sense. It doesn't say that there are no duplicates, but it doesn't matter, I guess. All right, so again, there's the size is very small, so notice that we're asked to find a path that visits all nodes. So there's a very famous kind of path which also visits all nodes, but exactly once, not multiple times, which is called a Hamiltonian path. Don't worry if you don't know this. I'm sharing the article. This is a very famous problem. So the problem is to decide whether there is a Hamiltonian path on a given graph, and this is one of those NP complete problems, which means that there is no known polynomial solution to this problem, and not only it is unknown, but we believe that there is none. And notice the relationship to our problem, because if you solve our problem, which gives you the length of the shortest path that visits all nodes, so if the length is n minus 1, that means that you're visiting every node exactly once. So that means that there is a Hamiltonian path. And if it is greater, then it means that there is not. So that means that if you solve this problem, you solve the Hamiltonian path problem. So that means that there cannot be a polynomial time algorithm for our problem, because otherwise we would find a polynomial time algorithm to solve the Hamiltonian path algorithm, which is not possible. Or, well, if we found that, we would find a revolutionary result in the history of mankind, actually. Anyway, so what do we do with this? So yeah, this is just so that we don't waste our time trying to find a polynomial solution. This is already hinted by the fact that the size is, so the graph is tiny. So usually when the graph is tiny, it's because there is no fast algorithm and you have to do some exponential time solution. So if you were to find a path without duplicated nodes, then you could search for all permutations. So 12 factorial is a pretty big number. So going over all the permutations would not be very efficient, but it's a little on the high side for LeetCode, 500 million, so 500 million. But if you do a backtracking algorithm, then you could actually it will probably run in time. So my first approach to this problem was to actually use backtracking, which is a little hard to predict how long it will take. So I tried that and it turned out that it was too slow. I got TLE. I solved around almost 40 test cases out of 50. And I use a technique which is that you keep track of the best result that you found so far, and then whenever you exceed, you already found a length that is it's not going to improve the result that you found so far, then you stop searching. But then the problem became to find an upper bound of the length, and for that maybe we can try to think a little bit. So the example 1 is a graph that looks like this, and notice that we start from here, we go here, then we go down and up again, and then we go down, so the length is 4. So if we call this 0, 1, 2, and 3, then the path is 0, 1 to 0, then to 2, then to 0 again, then to 3. It's 1, 2, 3, and 4. All right, so notice that we can generalize this kind of graph. This is what's called a star graph, which is also a tree, but you have a central node, and then you have leaves, and so on all around here. And so let's say that this has size n. So it's easy to see that the solution will have the same structure. So you start by any of the nodes of the leaves, and you move here to the center, and then for every other leaf you have to move there and then move back. So you do that for all of them until the last one, where you only have to go and you stay there. Okay, so since this is a tree, then that means that the number of edges, so the edges are n minus 1, and we go twice over every edge except 2, right? The first one and the last one. So this is the length here as a function of n for this kind of graph, for the star graph, right? And so this is 2n minus 4. Notice that here we assumed that there were at least 3 nodes, right? Because for us to go here and then here, we assumed 3 nodes. So this is for n greater than or equal to 3. The other cases are very trivial. Actually, if you have 1 or 2 nodes, then the length is obviously either 0 or 1. Anyways, so okay, so this gives us an upper bound. So, well, actually a lower bound. But notice that we could think about DFS traversal of any graph, and that will give us a spanning tree of the graph, because the traversal, if you think about only the edges where you find an unvisited vertex, then you'll have a tree that looks maybe like this, not necessarily a binary tree. And so notice that you can go over all the edges. So when you do the DFS traversal and you get to, for example, here, for example, you can go to, you can have a loop, a cycle, but since this is an already visited edge, you don't, this is a back edge, so you don't count this. But once you visited this node, then you go back and you go back here, then you move down here and here, and then you go back. So what this means is that at most you're gonna go over each edge twice, and since this is a tree, the edges that go to nodes that have not been visited before form a tree. So that means that there are n minus 1. So this means that the length of a graph of size n is at most 2 times n minus 1, right? Because like we said, there are n minus 1 edges, and we go twice over each in this traversal. So that gives us an upper bound. And notice that we can also have this optimization of subtracting 2, because, for example, here, instead of starting from the root, we could start from this leaf, and then we save the distance to this node, and then in the end we also don't need to go back. So this means that this is not only this, in some sense it's a tight bound. So for every graph, it has to be, the length has to be less than or equal to this, and in some graphs this is the answer. But in any case, notice that n here could be 12, and let's say that you have about 10 neighbors for each node. If you're doing a backtracking, then this 2n minus 4, which is the maximum length, if n is 12, is going to be 20, right? So 10 to the 20 is a very big number. So this is a kind of an upper bound, which tells you that the backtracking algorithm is probably going to be too slow. Again, this is an upper bound, so in order to convince yourself that it's going to be too slow, an idea would be to think about a kind of graph where you achieve this number. And I think that if you have something like this, you have an initial node, and you have here some kind of complete graph, but then you have some other node here. If you first start going to the complete graph, you could end up moving around the complete graph without ever reaching this outside node. And I think in that, so this can have size 10. So I think that could be too slow for this problem. But anyway, so now stepping back and thinking about this problem. So like I said, this is related to Hamiltonian paths, and there is a well-known way of solving Hamiltonian path that is better than going over all the permutations or the backtracking, which is based on dynamic programming. So based on dynamic programming, and it's based on bit masking. So because you can think of a subproblem as considering a subset of the vertex that you have already visited, and so your current node. So then you have to consider all the nodes that you haven't visited yet, and then you solve the problem recursively for those nodes. You mark the new node as visited, and so on. And if at any point you reach a subproblem where you have visited all the nodes, then that means that you found a Hamiltonian path, and that's good. And if you don't, then there was no Hamiltonian path. But here the problem is that you can move to nodes that you have visited already, right? So what do we do? Well, think about it. Does it make sense to keep going over nodes that you have visited? Eventually, why are you moving? Eventually, you want to move to a new node, to a node that wasn't visited, right? Otherwise, you'll never finish. Eventually, you have to move to a node that you haven't visited yet. And so if you're eventually going to move to that unvisited node, isn't it best the shortest path, the overall shortest walk or path will be composed of a shortest path? You want to go in the shortest path to that node, right? So that means that we can do something similar to what we did to what we were saying about the Hamiltonian path with the bit mask. But instead of considering the edges, we can consider the cost of the shortest path to the unvisited node, right? So the solution becomes just the same as a bit mask. So, but we have to pre-compute the distance between every pair of nodes, and one algorithm to do that is called Floyd Warshall, and is one of the most elegant algorithms there is. So we want to compute a matrix that gives us that is the shortest distance from I to J. And the algorithm itself is uses dynamic programming in a sense. So initially we want to know the distance between I and J without any intermediate nodes, right? So that means that the dist from I to J is going to be either 1, 0, or infinite. 1 if I J is an edge of the graph, right? Because there's no intermediate node in the path between I and J, and the cost is 1. 0 only when I is equal to J, and infinitely otherwise. Right? And then we're gonna do this for K so we are going to find the distance between I and J going over node K, right? As the minimum between the distance from, so we either, the minimum between I and J is either the current minimum, which at every step of this iteration is going to have the minimum distance considering all the nodes from 1 up to K minus 1, but not including K. And now we want to know if going from I to K and then from K to J is shorter, right? And that will give us the shortest distance from I to J from all, considering all intermediate nodes, now including K, from 1 up to K inclusive, right? And if we do that for K up to N, we'll finally have the distance from I to J, considering all intermediate nodes. So that is the idea behind the Floyd-Warshall algorithm. It's a very famous algorithm. The code is very simple, but I wanted to explain why it works. I'm gonna share cool idea. Yeah, it's a cool Good problem, I think. Okay, so let's do what we said. So we want to pre-compute the distance, the minimum distance between all pairs, and here we said that, well, initially if I is equal to j, then the distance is 0, else it is infinity. Then we go over all the edges, and the distance there is 1. And now we do the algorithm that we explained. So the distance from I to j is the minimum between the distance from I to j and from I to k plus the distance from k to j. So this is it. And now we have the distance from the minimum distance from any pair of nodes. All pairs shortest path is called, this problem is called. And now we want to do the memoization, the recursive function, to find the minimum distance starting from node u, and with this set of visited nodes, which is going to be at bit mask. So, and let's say that all the nodes are going to be represented by this bit mask that has n on bits. So if visited is equal to all the nodes, then there is nothing else to visit. There's no more edges to visit. So, and we visited them all. Otherwise, we want to find a new node, an unvisited new node. So, and any of them is available, and so we want to know if B is unvisited, and if it is unvisited, then we're going to find the minimum distance from there, and we want to mark this as visited with the XOR, which toggles that bit, and we want to, like we said, we want to add the cost of going from U to B in the shortest path, and we want to minimize this. Of all the next nodes, we want to find the one that gives us the minimum. So there must be one, at least one, so because otherwise we would be in that case, and so yeah, so we have to consider all the possible start nodes. We mark that one, we consider all starting nodes, and this should solve the problem. and it does. And there we go. Cool. So let me share my solution. So maybe I can explain the recurrence relationship without the bit set notation in a more mathematical notation. So what we said is that so the minimum distance was equal 0. Well, I forgot here to describe the parameters. So this is visited, or yeah, let's call it, for conciseness, let's call it bis. So let's consider this as a set. Whoa. So this is 0 if the size of visited is n. So we have visited them all, and otherwise we want the minimum of all the all the b's. Let's say this is 1 based. We want the minimum and yes, and we want b, so b to not be included in visited. Okay, so that's gonna give us all the nodes B that are not visited, and so then we just consider recursively the min distance from B and visited, and this is the union with the node B, plus the distance that we calculated from U to B. So yeah, so this is the same thing that we wrote in the code, but so it's this, but with a mathematical notation, without the bit masks. So maybe it's good to see it both ways. If you are not familiar with the bit masks, this helps you understand what we're doing in terms of sets, and then you can think about the so this is the same as doing the union in this case. So we are adding element B to the visited set, and this is checking if the B bit is on, or if it's off actually. So yeah, this was a good one. Hey, Lucia. Cool cat. Yeah, so that's all I have for today. It was a nice, pretty nice problem from LeetCode. Cool daily, and see you in the next one. Bye bye.